What specific problem does the Mulformer algorithm aim to solve in the context of olfactory perception, and what gap in existing research does it address?
The Mulformer algorithm aims to solve the problem of aligning representations of odorant chemical structures with human olfactory perception, specifically investigating whether these representations can predict human perceptual experiences without requiring extensive labeling by experts. It addresses a significant gap in existing research, as human olfactory perception has been underexplored compared to other sensory modalities, and there is no universally accepted method to quantitatively or qualitatively describe odorants. Previous models relied heavily on expert-labeled data, which is labor-intensive and introduces subjective biases, while Mulformer utilizes a transformer-based architecture that leverages implicit supervision from large datasets of chemical structures. This study provides the first empirical evidence of the alignment between odorant representations encoded by transformers and human olfactory perception, highlighting the potential of using pre-trained models to predict perceptual experiences from chemical structures.
How does the proposed Mulformer model work? Please illustrate step by step, from how it processes chemical structures to how it generates odorant representations.
The Mulformer model processes chemical structures by first encoding them using SMILE's Simplified Molecular Input Line Entry System strings, which represent relevant chemical information such as atom types and bonds. Once the SMILE strings are inputted, the model extracts a 768-dimensional vector from the last layer of its transformer architecture. For multi-component odorants, MC odorants, the model averages the extracted representations across all individual monomolecule components within the mixture. The resulting odorant representation is structured as a matrix where each row corresponds to a unique odorant, allowing for a comprehensive representation of the chemical structures. This process enables Mulformer to generate odorant representations that can be aligned with human olfactory perception, despite not being explicitly trained for this purpose.
Can you provide a simple yet illustrative example that demonstrates the inner workings of the Mulformer algorithm? Walk through the algorithm's main steps with this example.
To illustrate the inner workings of the Mulformer algorithm, consider the example of encoding a single odorant, such as vanillin, which has a specific chemical structure represented by its SMILE string. The first step involves inputting this SMILE string into the Mulformer model, which utilizes a transformer-based architecture to process the chemical information. The model then extracts a 768-dimensional vector from the last layer, capturing the relevant features of the odorant's chemical structure. For multi-component odorants, the algorithm averages the representations of individual molecules within the mixture to create a comprehensive representation. Finally, these extracted representations can be used to predict expert-assigned labels or human perceptual ratings, demonstrating the model's ability to align chemical structures with human olfactory perception, even without explicit training on perceptual data.
What are the theoretical or practical benefits of using the Mulformer method over traditional supervised models in modeling olfactory perception?
The Mulformer method offers several theoretical and practical benefits over traditional supervised models in modeling olfactory perception. Firstly, it utilizes a self-supervised approach, which eliminates the need for extensive labeling by experts, thus reducing the time and effort required for data preparation. This is particularly advantageous given the subjective nature of olfactory perception, which can introduce biases in expert labeling. Secondly, Mulformer demonstrates a high alignment with human olfactory perception despite not being explicitly trained for this purpose, achieving significant correlations with human perceptual ratings and similarity scores. Additionally, it captures perceptual relationships between odorants effectively, suggesting that it can predict similarities more accurately than models reliant on predefined descriptors. Lastly, the model's ability to extract relevant physiochemical features from chemical structures further enhances its predictive capabilities, making it a valuable tool for both chemists and neuroscientists exploring olfactory perception.
How was the Mulformer method validated or tested in your research? Discuss the datasets used and the evaluation metrics employed to measure its performance.
The Mulformer method was validated through a series of experiments using multiple datasets, including the Leffingwell-Goodsent dataset for expert-assigned labels, the Keller and Sauger datasets for continuous perceptual ratings, and the Ravia and Snitz datasets for similarity ratings between odorants. Each dataset provided a unique perspective on the model's performance, allowing for a comprehensive evaluation of its predictive capabilities. The evaluation metrics employed included the micro-averaged ROCAUC score for multi-label classification tasks, the normalized root mean squared error, NRMSE, for regression tasks, and the Pearson correlation coefficient, CC, to assess the linear correlation between predicted and actual values. These metrics enabled a detailed analysis of how well the Mulformer representations aligned with human perceptual data, demonstrating its effectiveness in predicting both expert labels and human ratings, despite not being explicitly trained for these tasks. Overall, the results indicated that Mulformer achieved high alignment with human olfactory perception, particularly in predicting similarity scores, showcasing its potential as a robust model for understanding odorant representations.
What specific results were achieved with the Mulformer model, and how do they compare to the baseline models like OpenPalm and DAM?
The Mulformer model demonstrated significant results in predicting expert-assigned labels for odorants, achieving high ROCAUC scores and outperforming the DAM model, which relies on 15 physiochemical descriptors. However, it performed slightly worse than the OpenPalm model, which is trained end-to-end with supervision on the same dataset. In predicting continuous perceptual ratings, Mulformer showed comparable performance to OpenPalm and outperformed DAM in the Keller dataset, although it underperformed in the Sauger dataset. Additionally, Mulformer exhibited a high correlation with human perceptual similarity ratings, achieving correlations of R equals 0.64 and R equals 0.66 for the Snitz and Ravia datasets, respectively, significantly surpassing the performance of the DAM model. Overall, while Mulformer was not explicitly trained for these tasks, it still demonstrated a strong alignment with human olfactory perception, indicating its effectiveness in capturing perceptual relationships between odorants.